Hi, my name is Charles Edler, and this is my Lab 5 of my own adventure. So to enter this lab, we decided to do a falling slinky example. And the purpose of the lab is to predict the motion of a falling slinky while tracking the effects of its surroundings, like when it's falling down, when it makes contact, and then reaches the full ground. The goal is to determine whether the bottom of the slinky stays stationary during the drop. And although we observe some fluctuations, the bottom of the slinky remained stationary throughout the experiment. Some principles and equations we must know is Newton's second law, which is the change of momentum is proportional to the force applied. Our net force here would be the force of tension on the slinky and the force of gravity allowing the slinky to move down. And then gravitational force and tension force, the force of the slinky is equivalent to tension, which is the opposite to the gravitational force. And since the gravitational is negative mgh, the tension has to be positive mgh to allow them to cancel out. So, let's see if the video works. All right. So this is the falling slinky that we used to record, and you can see that the bottom of it stays relatively stationary as it is being dropped. It's a very slow video. And then the moment it makes contact, the whole slinky begins to move down with it. And so with these, we also have the initial position, which is basically zero, initial velocity, which is zero, the spring mass, which is 0.218 kilograms, and then the calibration height, which is based on this person's height, we recorded as 1.75 meters, which is about 5'7". Then for the coding for this experiment, we have the ball's mass, the initial positions, uh, the time change that'll go in the loops, the force of gravity, and then we have J hat, which is basically just saying during the calculation over here with finding tension is that we're in the positive y direction. And we have the drag force constant being 75. And then for the first loop, which is the amount of time it takes at the top of the slinky to reach the stationary bottom, which this right here is the negative mgh. The force of tension, which is just the negative of the force of gravity, and then the net, which is just canceling it out. Then we had the velocity update formula, the position update formula, and the time update formula. And over here is the second loop, which happens after the slinky makes contact with itself at the bottom, which has the same exact formula for tension. However, we also have to include drag at this point, and then the net would be the combination of drag and the force of gravity. And then we also have the update for velocity and position as well, and time. The results for this experiment, the bottom of the slinky remains in place for around 5.5 seconds, after which the top of the slinky reaches the bottom. Once top reaches the bottom, the whole slinky falls towards the ground altogether, which we can see right here. The moment it makes contact right here, the bottom of the slinky then goes to the ground after remaining stationary. And the possible errors we could have this experiment is the observed motion was influenced by external force not accounted for, or the placement points were not precisely placed on the tracker, which can cause some error in the graph. And then for discussion questions, we decided to ask what if the slinky has a counterweight at the bottom, like right here, and we concluded that if the weight allows for the tension and gravitational force to still remain equal, or the spring is long enough, the bottom of the spring will still remain stationary even after it is dropped. Thank you for watching.